Hello everyone and welcome to our calculus notes for section 5.1. Today we're going to be talking about the natural logarithmic function and differentiation. So first off, here's the graph of the natural log function, ln of x. And I'm zoomed in on the most interesting parts of the graph here, and we have our x-intercept here of 0, and that happens at x equals 1. Now, the way this goes, we have a vertical asymptote here at 0, and as this function approaches 0 from the right-hand side, this value goes to infinity. Now, over here, as x goes to infinity, the y value also increases to infinity. So, just a review of a couple logarithmic properties before we get into differentiation. The natural log of 1 is, as I just said, 0. The natural log of a times b can be separated or expanded to be the natural log of a plus the natural log of b. Okay, and notice this can go forwards and backwards here. Now the natural log of a to the nth power is going to be n times the natural log of a. So we can think this is going to be a times a times a times a, which would be the natural log of a plus the natural log of a plus the natural log of a, which would be n times the natural log of a. And this, of course, can go backwards as well. And the natural log of a quotient, a over b, is going to be the natural log of a minus the natural log of b. And this can go backwards as well. So in these first examples, we just want to expand each logarithmic expression. So here, natural log of 10 over 9, well, it looks exactly like number 4, so this is going to be the natural log of 10 minus the natural log of 9. So this would be fully expanded. In letter B, here we have the natural log of the square root of 3x plus 2. So what we want to do with the square root is change this into an exponent form. So it's going to be the natural log of 3x plus 2 to the 1/2. Okay, from here, now we have a direct representation of number 3. Okay, because we're taking the natural log of this entire value. So this is going to be 1/2 times the natural log of 3x plus 2. Now we ask ourselves, is this completely expanded? Well, we have a sum inside. We're taking the natural log of a sum, and you can see we don't have any properties for that, and so this is expanded. All right, letter C. Now we have the natural log of 6x divided by 5. So we have a couple things going on here. We have 6 times x and then divided by 5. So let's just apply rule number 4 first with the quotient. So this is going to be the natural log of 6x minus the natural log of 5. And now you can see it's not completely expanded because we still have 6 times x in here. So let's expand this part using number 2. So it'll be the natural log of 6 plus the natural log of x minus the natural log of 5. Okay? And you could go straight from here to here. If you can see, multiplying means you're going to add, and then dividing means you're going to subtract. All right, letter D, a lot of stuff going on here. Okay, so you just kind of have to take them a little bit at a time. So first, I'm going to deal with the quotient right here. And so I'm going to write the natural log of x squared plus 3 squared minus the natural log of the denominator now, which is x times, well, I'm going to change this radical into an exponent. So x squared plus 1 to the 1/3. Okay, so now we can expand each of these. So here we have an exponent inside the natural log function. So we get 2 natural log of x squared plus 3. And here this is a sum, so we're done expanding that. And now we have minus. I'm actually going to put parentheses here so that we can just deal with this by itself. So here we have multiplication and an exponent. So let's deal with the multiplication first. So we'll do the natural log of x plus the natural log of x squared plus 1 to the 1/3. Okay, and now we have an exponent inside here, so the 1/3 will come out. And so the 1/3 will multiply in front, and it's times the natural log of x squared plus 1. And then you can choose to distribute the negative if you would like. So we have 2 natural log x squared plus 3 minus natural log of x minus 1/3 natural log x squared plus 1. Okay, so that's basically how we use the properties of the natural logarithmic function. Next, we're going to talk about the derivative of the natural logarithmic function. And we're going to do this first by approximating the derivative of f of x equals natural log of x using our limit definition of the derivative. So the limit definition of the derivative, for review, is the limit as delta x approaches 0 of our function, so natural log of x plus delta x minus the natural log of x, so those are the change in your y values, over delta x, which is your change in your x values. So again, we're just finding the slope of the function. Now, what we're going to do to approximate this is we're just going to let delta x be some small number. So let's just say like 0.001. That'll be small enough for our purposes. So if we let delta x equal 0.001, this formula or function for the derivative is going to be the natural log of x plus 0.001 minus the natural log of x over 0.001. So what we want to do is figure out the slope now of the natural log function at 2, 3, 4, and then eventually at x. So if we look back here, so at x equals 2, we're trying to determine what is the slope of the function. At 3, what is the slope of the function? At 4, what is the slope of our function? So that's what we're looking at. And so all we need to do is substitute 2 in for x into this equation, and that's going to give us an approximation. I'm going to use Wolfram Alpha to calculate this. So we're going to want to parentheses around the numerator here. So we'll open that up. And now we have the natural log of x plus 0.001. So that's 2 plus 0.001 minus the natural log of x, which is just 2. We'll close the parentheses for the numerator and divide it by 0.001. And here we get a result of 0.499875. So I'll just put 0.4999. Okay, let's try this again with 3 and 4. You can try that on your own and see what you come up with. Okay, so let's see if there is any way that we can find the derivative of f prime of x by looking at these examples. Now, what I want you to do is say, how is 2 related to f prime of 2? How is 3 related to f prime of 3? And how is 4 related to f prime of 4? Okay, well this is really close to 0.5, right? And how does 0.5 relate to 2? Well, 1 over 2 equals 0.5. This right here, hopefully you can recognize as 1/3. So if we plug in 3, we get 1/3. This is really close to 0.25, which we know is 1/4. So have you detected the pattern? F prime of 2 equals 1/2. F prime of 3 equals 1/3. F prime of 4 equals 1/4. So F prime of x equals, you guessed it, 1/x. And there we go. So we used kind of a numerical process to kind of cheat our way to figure out what the derivative of the natural log function is. And here it is in a mathematical formula. The derivative with respect to x of natural log of x equals 1/x. And note that x has to be positive because that's what the natural log function is. It's always positive. If we want to use our u substitution, we could see the derivative with respect to x of natural log of u is 1/u times du dx, or u prime over u. So this is really if we needed to use the chain rule. Okay, so this is really the one that you want to focus on right here. So let's try a couple of these. Here, the derivative with respect to x of natural log of 2x. So now I can see that my u equals 2x here. And so the natural log function, the derivative, is always u prime over u. Okay, so what's u prime? Well, the derivative of 2x is 2. And then what's u? Well, that is 2x. And so if we were to simplify this, we have 1/x. Okay, so that constant multiple in there didn't change what our derivative is. Let's try letter B. Now we have the natural log of x squared plus 1. So again, we have this u idea where u equals x squared plus 1, and we would know u prime is 2x. And so this becomes u prime over u, which is 2x over x squared plus 1. And no simplifying here. There's your final answer. For letter C, now we have the derivative of x times the natural log of x. Well, in this case, this is a product. So we are going to have to use the product rule, which remember is 1d2 plus 2d1. So the first function is x times the derivative of natural log of x, and then plus the second function, which is ln of x, times the derivative of x. Okay, so just a little bit of product rule there for you. And now let's take our derivative of natural log of x, which is 1/x. So this is x times 1/x. And then here, this is going to be the natural log of x times the derivative of x, which is just 1. So x times 1/x equals 1. And then natural log of x times 1 is just natural log of x. And there's your derivative. All right, in this problem, now I have the natural log of x cubed. So if we were to think about this, u in this case would be the natural log of x. And so we're actually looking for the derivative with respect to x of u cubed. And so this is going to be kind of a chain rule problem. So remember, this is going to be 3 times u squared times the derivative of u. Okay, so looking at this, it's going to be 3 times ln of x squared times the derivative with respect to x of ln of x. So the derivative of ln of x is 1/x, so we're left with 3 times natural log of x squared times 1/x. And if we wanted to just put these together, you're probably going to see the answer written like this. 3 times natural log of x squared over x. Okay, so this one, we had to use the chain rule, and not where we had natural log of u, but where the natural log was actually u, and it was u cubed. All right, so we learned something new about the natural logarithmic function, that its slope is always the reciprocal of whatever x value that you plug in. So looking back at this graph, if we're at x equals 2, we know the slope is 1/2. If we're at x equals 5, we know the slope is 1/5. And so that's a pretty powerful little connection there. All right, moving on. So now we're going to use logarithmic properties to aid in our differentiation. So of course, it always gets a little bit tougher. So the first thing you want to do is try to expand this form. So use our properties. Okay? So our first one is f of x equals natural log of the square root of x plus 1. And so first thing we want to do is change the radical into an exponent. And we know the exponent then can come in front of the natural log and multiply. And so this is what we're taking the derivative of right here. So f prime of x. Okay, well here's our constant. So that's just going to stay out in front. And now we need the derivative of the natural log of x plus 1, which remember is u prime over u. And u in this case is going to equal x plus 1. So u prime is just 1 over u, which is x plus 1. And so if we wanted to simplify this, we would have the derivative 1 over 2 times quantity x plus 1. All right, let's try our next one. First thing we want to do is expand our natural log function here. So I see x times this divided by this, so we get the natural log of x plus, okay, then we have x squared plus 1 raised to the power of 2. So let's go ahead and bring that 2 out in front. So we have 2 times the natural log of x squared plus 1. And then divided by, so that's going to be minus. And we know 2x cubed minus 1, the square root is going to be to the 1/2. So let's bring the 1/2 out in front right away. And then natural log of 2x cubed minus 1. Okay, now let's go ahead and find the derivative after expanding. So the derivative of natural log of x is 1 over x. Here we have our constant, so it'll be 2 times, okay, and it's got to be u prime over u. So the derivative of x squared plus 1, which is 2x, divided by x squared plus 1. So u prime over u. And then minus 1/2 times, well, the derivative of 2x cubed minus 1, which is going to be, let's see, 3 times 2, which is 6x, and then 3 minus 1 gives me 2, over u, which is 2x cubed minus 1. Now from here, we could multiply these in, and so we're left with 1 over x plus 4x over x squared plus 1 minus, let's see, the 6 and the 2 will cancel. So we have 3x squared over 2x cubed minus 1. And here's your derivative. All right, we just want to do a couple more examples here using derivative rules to differentiate the following equations. So it's really just seeing how we can see natural log function in some of these other functions. So this would be the natural log of x squared, and so we would have to use our properties first and get 2 times the natural log of x, and then take the derivative, which would just be 2 over x. In this case, notice this is the natural log of x squared. So we can't really expand this at all. Instead, we have to use the chain rule. So y prime is going to be 2 times the natural log of x to the first times the derivative of the natural log of x. Okay, so that's the chain rule. And we can clean this up a bit. 2 ln of x, and then the derivative of natural log is 1 over x. So we'll just rewrite this as 2 ln of x over x. And for example C, notice we have a quotient, but the ln is not in front of it. So we can't differentiate like we did up here in letter B. Instead, this is going to call for the quotient rule, which we remember as low d high minus high d low over low squared. Okay, so let's find y prime here. So low d high. So the low function is x squared. The derivative of the high function is 1 over x minus high d low. So the high function was natural log of x times the derivative of x squared, which would be 2x. And this would all be over low squared, or x to the 4th. Okay, and let's just clean this up a little bit. So here, x squared times 1 over x is just x. And we'll move the 2x out in front, so 2x ln of x over x to the 4th. And now you can see we have a common factor there. So if we simplify this, we're going to get 1 minus 2 ln of x over x cubed. Okay, so we can take the x out of all of those, and this is our final answer for the simplified derivative. Now our next topic is something called logarithmic differentiation. And basically what we're going to do is use logarithms to differentiate non-logarithmic functions. So if we look at this function right here, you don't see any natural logs. Okay? But if we tried to differentiate this, it could be pretty difficult. Okay, we could use the quotient rule, and it might take a lot of steps. But I'm going to show you how we can use logarithms to help us with this process. So the first thing we want to do with this function is take the natural log of both sides. So we'll just say the natural log of y equals the natural log of this entire side. So x minus 2 squared over the square root of x squared plus 1. Okay, so that's the first step, taking the natural log of both sides. Now we want to use log properties to expand this natural log function. So on the left side of the equation, we still have the natural log of y. Okay, and this is going to be the natural log of, well, the 2 is actually going to come out in front. And it'll be of x minus 2. And then it's divided by, so it's going to be minus, and here's a 1/2, so 1/2 natural log of x squared plus 1. Okay, so we used our log properties to expand the log function. And now what we want to do is differentiate this. And we end up differentiating the entire thing. Okay, so we want to take the derivative with respect to x of all of this. Okay, so the derivative of natural log of y is going to be y prime over y. Okay, this one is going to be 2 times the derivative of natural log of x minus 2. Okay, which is just going to be 1 over x minus 2. Okay, and then minus 1/2. Well, the derivative of natural log of x squared plus 1, remember u prime over u, so it's going to be 2x over x squared plus 1. Okay, once we've differentiated, now we want to simplify this. So we still have y prime over y. Here we have 2 over x minus 2. Leave a little bit of space here for our next step. And then we have 1/2 times 2, so those are going to cancel. And we're going to be left with x over x squared plus 1. So minus x over x squared plus 1. And what we want to do is get this to be a common denominator so that we can add these two terms together. So that's why we left a little bit of space here. So here we have an x minus 2. Here we have an x squared plus 1. So we're going to multiply this side by x squared plus 1 over x squared plus 1. And this one we're going to multiply by x minus 2 over x minus 2. Okay, so common denominator. This is going to give us y prime over y. So let's go ahead and distribute this. So we're going to get 2x squared plus 2 minus x squared plus 2x. Okay, so don't forget about that negative. So it's minus x squared plus 2x, all divided by x minus 2 times x squared plus 1. Okay, and we can still simplify this a little bit more. Let's move up to the top here. So y prime over y equals, well, 2x squared minus x squared is just x squared. And then we have plus 2x. And then plus 2. And this is divided by x minus 2 times x squared plus 1. Okay, and at this point we will just want to stop and think, well, what are we trying to find? It says use logarithms to differentiate the non-logarithmic function. So really what we're looking for in all of this is y prime. Looking for y prime. Do you see y prime? Yeah, it's right there. So we almost have y prime if it weren't for the divided by y. So we have to think, how can we get y prime by itself? Well, this is the next step. We want to solve for y prime, and we're going to do that by multiplying by y on both sides. Okay, so the y cancels there. We're left with y prime equals y times x squared plus 2x plus 2 over x minus 2 times x squared plus 1. And now what we want to do is get y prime just in terms of x. So here we're going to substitute for y. Okay, well, what are we going to substitute? Well, y equals all of this. So now we need to substitute that in for y. So we get y prime equals x minus 2 squared over the square root of x squared plus 1, and then times the rest of this, x squared plus 2x plus 2 over x minus 2 times x squared plus 1. Alright, and the final step now is to simplify this. So here we can see an x minus 2 squared and an x minus 2 on the bottom. So I can cross that out and get rid of the 2 there. And now I can see x squared plus 1, and here's an x squared plus 1. So we're going to add these exponents, the 1 and the 1/2. So we're left with x squared plus 1 to the 3/2 in the denominator, and in the numerator we have x minus 2 times x squared plus 2x plus 2. And there is our simplified derivative. Okay, so let's just review the process real quick. Take the natural log of both sides, use the log properties to expand, differentiate the entire left and right sides, and then simplify as best you can. Solve for y prime by multiplying by y on both sides. Okay. Then substitute the function in for y and then simplify, and there you have your derivative. And one final example, we want to find the equation of the tangent line of y equals x squared plus ln of 2x minus 5 at the point 3, 9. So if you want to find an equation of a tangent line, we need to first find the slope. And to do that, we need to find y prime. So here, derivative of x squared is 2x. The derivative of the natural log of 2x minus 5. Okay, it's going to be du, so 2 over u, which would just be 2x minus 5. And so this is our slope. And now what we need to do is find the slope at 3, 9. We'll plug in our x value of 3, so 2 times 3 plus 2 over 2 times 3 minus 5, which is going to be 6 plus 2 over 6 minus 5, which is 1, which is 8. So our slope is 8. Sometimes we refer to this as m. And now we'll use our point slope form to determine our equation. So y minus y1, which is 9, equals m, which is 8 times x minus x sub 1, so x minus 3. And we'll just finish this out now. Y equals, so we have 8x, and then we have minus 24, and then plus 9. So all in all, we have y equals 8x minus 15. So this here would be the equation of the tangent line at y equals x squared plus natural log of 2x minus 5 at the point 3, 9. All right, so that is logarithmic differentiation.